Welcome to the SAMPE question and answer sessions for emerging materials and process. And I thank you for joining us. I would like to make all of you aware this session will be recorded and posted on the SAMPE website for on-demand viewing. If you have questions throughout the duration of the sessions, please type them in the Q&A feature around the panel of your Zoom meeting window. I'm going to give a little bit of introduction of myself. My name is Joseph Koo. I'm a research professor at the University of Texas at Austin. I have been conducting polymer nanocomposite research for extreme conditions for a number of years. So my research group has been doing nanocomposite for extreme condition. Let me explain what's extreme conditions. Mostly deal with solid rocket motors or thermal protection systems. So that's one area that my research group works on. We also have done a fair amount of work on additive manufacturing. We have been doing high performance thermoplastic, and I think recently we received 2 research grants from government to do thermosets for additive manufacturing. That's what we have been doing. So I'm going to introduce you to actually the 5 panelists in this particular session. I'm going to start with actually speaker 1. Speaker number 1 is John Gangloff. He is from United Technologies Research Center. Dr. John Gangloff is a senior research engineer at United Technologies Research Center in East Hartford, Connecticut. John works in the area of advanced materials and processing science, including the topics of structural and high temperature composite, advanced material joining, and AI, machine learning, enhanced composite design approaches. John has 25 plus peer-reviewed journal publication, as well as a conference proceeding and 3 patents and patent pending relating to advanced composite material with fuel cell electric vehicle technology. John is a 2014 received his PhD from University of Delaware Center for Composite in Mechanical Engineering. He has researched the topic of multifold process through porous media. Before joining UTRC, John worked as a science and technology policy fellow in the U.S. Department of Energy, Field Science, Fuel Cell Technologies Office in Washington, D.C. on the topic of innovative hydrogen storage systems for fuel cell electric, like vehicles. The title of his talk is Low-Cost Glass Ceramic Matrix Composite for Harsh Environment Heat Exchanger Application. Okay, with that, I'm going to ask the first question. The first question from the audience is slide 11. What is the tape width and what pressures are required during the hot press step? John, can you answer those?
Thank you for the introduction. With respect to slide 11, so that slide is discussing our glass ceramic matrix composite manufacturing process flow. For this particular work, making these heat exchanger sub-elements as presented in the SAMPE virtual series, our length scales are on the order of, say, 3 inches by 6 inches on that subscale. Our compression molding pressure is proprietary, but we can say that it's sufficient pressure to initiate the flow of molten glass to form the heat exchanger subelements.
Anything else you want to add for question number 1?
Just that I think one of the keys, especially I highlighted in yellow color on slide 11, is the manufacturing process that we presented in this slide deck. It's similar process to working with thermoplastic polymer matrix composites. So it's kind of, there's some analogies from the thermoplastic polymer matrix composites world that we could be applicable to the forming of glass ceramic matrix composites.
Okay, well, the second question is still slide 11. What factors during processing enable control over porosity? John?
So at this point, we don't have actual control over the porosity. What we are trying to do is develop the process conditions so that we can get 99.5% glass filling of all the evacuated space inside of the heat exchanger subelements. This is part of the research problem, right, is trying to figure out what process conditions we have available to that might be able to control the porosity, but this is ongoing development.
Okay. All right. So I probably will come back with some questions for you. I actually noticed you graduated from University of Delaware. Who was your advisor, John?
Oh, I was a student of Professor Suresh Advani.
Oh, I think I know. I think I know a few faculty actually at your university, your department. Okay, thank you, John.
Thanks.
All right, let me move on to speaker number 2. It's Florence Rinn. How to pronounce that word? Oxeon? Onen? Florence? How to pronounce that word?
Oxeon.
UN.
That's the company name, yes. Yes,
Oh.
exactly.
Okay. Florence obtained her Master of Science degree in Material Science and Engineering from European Engineering School of Material Science. That word I don't know how to pronounce. What is that? How do you pronounce that? University of Technology in Sweden.
Yeah, okay. You can say LTU. It's Luleå University of Technology. Yeah.
All right. From Sweden. Oh, I was in Sweden actually last year. I was in Stockholm.
Okay.
After working with failure analysis on composite parts at Airbus operations, she's now project manager in the product development department at Oxeon, and is involved in the development of new hacks. Okay, extreme. How do you pronounce that?
Textream. Yeah. Textream, as you said. Yeah.
Products and as associate processing. She is also involved in customer-driven projects as a technical support and in different research projects, analyzing benefits of using texture. Her actually paper title is Thin Ply Sheet Molding Compound Enable Thin Laminates with Properties as a Continuous Fiber. All right, so the first question actually came in as slide 11. How would pieces be stacked in production environments to ensure repeatable part performance? To ensure said repeatable thick parts required than parts produced during basic research conditions. Can you show slide 11? Not.
I will share the
Yeah.
screen.
Then you could actually use the slide and speak to that. Slide 10. Okay, go further down. Okay.
Can you all see that?
All right, so that was the question.
Yeah. So just to summarize a bit the background of this slide, in that research work, we have manufactured some plates that are made with thin ply SMCs. And in order to manufacture those SMCs, the tapes flake or the tapes pieces were placed in a random way. They were placed manually in that work, having equivalent laminate with full coverage, and then several equivalent laminates were stacked together to have the plate with the thickness required, or the number of tapes required. So the question was more about what happened in a production environment. So at Oxeon, we have developed a conceptual machine, automated machine, that is fed with our Textream tapes, thin tapes. And so that machine is actually applying the tapes randomly on a carrying support, carrying paper. And then the sheet is consolidated. And that's what we obtain, the thin ply SMC, basically, that we can directly use in a manufacturing process. The question was also about repeatability.
Thicker part.
Sorry?
I think there's, you finished the first part of the question. How about the second part for thicker?
Yeah, yeah, exactly. So for now, the work that has been done at Oxeon with this automated conceptual machine, this concept has shown that we are able to have a sheet thickness of 0.5 millimeter and still have good randomization, so good isotropy in different direction. Then some ongoing work is still performed now about repeatability and variability also, to really determine if the process is, in which extent the process is repeatable, and which tolerance we have on the properties. And then also the machine is can be further fine-tuned to see that we can achieve maybe lower thickness, as what we've done in the research work, to have an even better optimized randomization and then lower sheet thickness.
Good.
Yeah.
All right. I'm going to turn into a question number 2. Can you pull slide number 13? Because
okay.
Slide number 13.
Yeah, I will just.
I think the question was not for slide 13. Were samples of other materials produced at the same part thickness and wall and fiber volume? If so, what do you think about UHM-100-800 and the highest stiffest value? Okay, this is a slide. Okay.
Exactly. So in that slide, we were comparing the thin ply SMCs, so manufactured with the Textream spread to tapes, and some other SMC products that are either available in the literature or already commercially available. So the purpose of this comparison was also to compare the different material systems. So it's the specimens didn't have the same thickness, basically because for some SMC products that are manufactured with standard materials, a very thin sheet thickness is not achievable. So they had, those specimens had a higher thickness. And then, of course, the thin ply SMC, as we discussed, has a lower sheet thickness, down to even lower than 0.5 millimeter. The fiber volume fraction, I have the same answer here. Since it's different material systems, the fiber volume fraction was not the same, but every result was normalized with a fiber volume fraction of 57%, that is typically seen in the SMC products. Yeah, and then what was the second part of the question? Yeah, okay, about the stiffness
Right.
of the ultra high modulus fiber. So the UHM configuration that you see in red in the graph below, this was made with ultra high modulus fiber, pitch fibers. So if we just look at the stiffness value, of course, it has the highest stiffness because it's made with very stiff fibers. But the interesting part is also to compare the second graph, where we compare the stiffness of the SMC divided by the stiffness of the fiber itself. And here we see that for this configuration, which was made also with thick tape, we see that we obtain this ratio is lower than, for example, the blue specimen, which was made with very thin tapes of 20 microns. And this means that with the thin tapes, we are able to achieve a better exploitation of the fiber properties than with thick tapes. And that's what we see here, and that's what is interesting here.
Good, Florence. Thank you.
Yeah.
Right. I think you answered the question of flying colors also with the slide. Then I know what's going on. All right. Thank you, Florence. I'm going to move to the third speaker. It's the third speaker is Jordan Harris from, is it Vartega? Is that pronounced as Vartega?
Yes, that's correct. Vartega.
Vartega. I think I heard of the company. Jordan Harris is a product manager for Vartega's carbon fiber business. He is advancing Vartega's growth by identifying opportunities in new markets and leading technical development projects resulting in sales. Previously, as senior process engineer, he worked to scale Vartega's recycling technology and develop products particularly suitable for thermoplastic processing. Prior to joining Vartega, Jordan served as an R&D engineer at Infilchem Polymer, where he was critical in the advancement of a novel chemical-based recycling process to convert scrap polyurethane back into oil for reuse in the polymer. He holds a degree in chemical engineering from Michigan State University. I will ask you a question about Michigan State because I actually know a few faculties in there. So it will be after we finish all the questions. The title of his talk is Closing the Loop on Automotive Carbon Fiber Pre-Packed Manufacturing Scraps, Fender Case Study. The first question for you, Jordan, is did you do any void content fiber wet out analysis that may have affected your mechanical properties? All right.
Yeah, thanks, Joe. Thanks for that introduction and thanks for the question. We do apply some of those analytical techniques to look at those things, XCT for void content analysis, and we've utilized SCM to look at fiber pullout to determine adhesion between fiber and resin matrix. We didn't do that specifically for the work that was completed for this project. If I had to look forward and anticipate the reasoning behind that question, I would guess it related to the mechanical properties that we realized in this project as reduced with the recycled carbon fiber compared to a non-recycled fiber. So based on that work that we've done on looking at fibers in the past, we would expect that in this project, the reduction of the mechanical properties were due to poor adhesion between fiber and recycled fiber and the resin matrix system, mostly as a result of less than adequate resin removal in the recycling process, which was a function of a couple of challenges that we faced in the development work that we were doing to recycle prepreg material and convert that fiber into a form ideal for thermoplastic compounding. Those that have seen the presentation, the virtual presentation for SAMPE will know that outside of the work that we did that made it into the paper, we looked at additional testing with recycled fibers that had achieved a greater level of recycling, and due to that we were able to determine that mechanical properties between a recycled fiber and a virgin were nearly identical.
Good. Any other comments on question one? Jordan?
No, just that it's I think it's a good question. Void content, looking at that in molds is I think a little trickier sometimes to make connections between the processing and how the fiber is filling in the resin and in the mold, and how that impacts mechanicals. Whereas it's pretty clear using techniques like SCM to look at adhesion between fiber and resin that there's a significant importance of good adhesion, and it's pretty obvious to see when you have it and when you don't.
Okay, well, second question. You help me pronounce this word. What is this Solalysis EE?
Yeah, Solalysis, embodied energy.
EE. Wow, Solalysis EE seems very low. Is there some supporting data to show that low energy use for Solalysis?
Yeah, the embodied energy of the Solalysis process is quite low. And if you think about the energy requirements for producing a virgin carbon fiber, the polymerization, the spinning, carbonization, oxidation, all of those high energy processes that are required, none of that is necessary to produce a recycled carbon fiber. Vartega has a proprietary chemistry-based process for extracting and removing the resin from the fiber, and it's a process that certainly compared to producing virgin fiber is much lower energy. So specific data to back that up is somewhat proprietary to Vartega's process. So we produce that the information as it relates to our energy usage to University of Tennessee Oak Ridge National Labs to do the life cycle analysis, which is highlighted in our report. But corroborating data, it would be difficult because of the sort of unique nature of Vartega's process. But again, when you draw those comparisons to what it takes to produce a virgin carbon fiber, the embodied energy of a Solalysis process is quite low.
Okay, I have a question for you. Actually, since you're in Michigan State, do you know Professor Larry Drizel?
I know his name. I don't know him personally, but
Okay.
his name, especially in the composites world, pops up
Well,
quite a bit.
I know Larry quite well. How about Andre Lee?
That one I don't know.
He is also a professor at chemical engineering and materials. Okay, those are my questions for you. Thank you very much, Jordan.
Thank you.
Thank you. The fourth speaker is Daniel Merkel. He is from Pacific Northwest National Laboratory. Daniel is a material science at Pacific Northwest National Laboratory performing research in composite materials characterization at cryogenic temperatures for hydrogen storage application. Before he joined Pacific Northwest in 2016, Daniel was involved in basic research. What is that word? Metric elastomer at University of Wyoming. What does that mean, Daniel?
So is it liquid crystal elastomer? Is that the word?
Yeah, and metric.
Oh, pneumatic. Yeah, pneumatic.
Pneumatic.
Liquid crystal
What is that?
elastomers, yeah. So liquid crystals have liquid crystals have their own what they call mesophases, and pneumatic is a phase in the liquid crystal.
Well,
area.
thank you for teaching me because
Sure.
I didn't know that particular word. All right. I have some questions for you later on from University of Wyoming because I know somebody teaching University of Wyoming. All right. First question. What is the total amount of time to reach testing temperature of 20 Kelvin when you use the combination of liquid helium and liquid nitrogen? So that is the first question. Daniel?
Yeah, so that's a good question. I don't have real data on that one. One of the problems with using that method, it's not typically used to cool down cryostats because you have to make sure all the nitrogen is out of the system before you can start using helium to cool, because nitrogen will freeze once it gets below 77 Kelvin. Of course, helium's temperature is down by 4 Kelvin. So that's not commonly done because the nitrogen will freeze in the line and then cause a blockage, and then you won't get cooling anymore. So our system's kind of unique in that it's much larger than most cryostats, and so we've looked at this briefly, although we haven't done it yet. But one of the things we can do, and we plan to do in the near future here, is to take this approach where we first cool with liquid nitrogen, which would take something like 3.5 to 4 hours, I believe, to get to 77 Kelvin. And then we'd have to either evacuate the system or kind of let it air out, let the nitrogen escape before we start cooling with helium to get down to a lower temperature. And so in that process, I would assume it would take about 6 hours to do that based on what we know about the helium cooling time. We actually have this, I don't think this is in the presentation, and I'm pretty sure it's not in the paper, but we have recently developed a way to cool with helium, which is much more efficient. So I think if you look in the presentation, it takes something like 30 to 40 hours to cool. Maybe it's even 50 hours to cool with helium. We recently found a way to cool it with helium that's quite a bit faster, and so we should be able to get down from room temperature to 20 or even 4 Kelvin within 6 hours. And so from an efficiency point of view, time efficiency that is, it'd be much more efficient to cool with liquid helium from room temperature using this new method we've got now. And alternatively is also the question of cost. Helium's very much more expensive than nitrogen. I think it's
Mhm.
2 to 3 orders of magnitude more expensive. And so you know, if you forget time and you start thinking about cost, if you're on a limited budget, then I think that's our primary reason for looking at this cooling with nitrogen and then switching over to helium, because we think we can use, you know, maybe just a couple of liters of helium to cool down from 77 down the rest of the way to a lower temperature. So my projection is we'll say less than 8 hours, 6 to 8 hours to do that. You know, starting with liquid nitrogen and then cooling with liquid helium method.
Okay. How about question number 2? When do you anticipate have a modeling program that incorporates the pressure fatigue data? That's question number 2.
Yeah, so that's another good question. We know that this is an area of importance to industry and tank manufacturers specifically. The data is not out there for the cryogenic temperature ranges. And so this project here is wrapping up in the next couple of months. And, you know, we haven't obtained the fatigue data that this question is asking about, but we know that we want to do this in the future, and so I think this is going to be top priority for us in the next 2 to 3 years to obtain this data in the laboratory, and I think in parallel with that we would have the modeling effort to incorporate that information as well. And so some of the other things that we're developing that might go into this is some modeling effort around crack formation due to thermal cycling. There's also the, you know, pressure cycling, pressure fatigue that develops cracks over time in the composite specifically. So that's not really even considering the metal portion of these tanks. And so I think we can imply with the models that we have, we can imply some of the fatigue data, but you know, we don't outright have the fatigue data incorporated into our model, nor do we have the laboratory data to support the development yet. So I think in the next 3 years, I think we will have a significant effort towards developing the pressure fatigue data into the model.
Okay. Any other additional comment, Daniel? I have a question for you.
Sure.
You're from the University of Wyoming. Were you which department you actually did you graduate in U of Wyoming, or you just work in U of Wyoming?
Yeah, I graduated from the University of Wyoming from the mechanical engineering department.
Oh, who was the department chair in the mechanical engineering department?
So it switched over while I was there. When I was first there, it was Paul Dellenbach.
I know Paul Dellenbach a long time ago.
Oh, do you?
Yeah, I know Paul Dellenbach when he was a grad student.
Oh, wow. Okay.
Arizona State. Is that correct?
Yeah, I think that's right. Yep.
Yeah, that's why I said when I see this, where you graduate, I know a few people. So did Paul? He was a department chair, and he only a few years ago he is he retired? Is Paul retired?
No, he stepped down from department chair. My understanding is that he's still teaching, but in a limited capacity. I think he's now kind of moved up into some higher ranks of the engineering college. So I think.
Oh, okay. I need to shoot him an email.
Yeah.
I know Paul when he was a grad student. When I was a grad student too.
Yeah, that's awesome.
So that's why I said, oh, you're Wyoming in mechanical. I think another professor I know is younger. He's in materials. Is it the Freitag?
Fertig?
Yeah.
Yep. Ray Fertig, yeah. Yep, I know him as
Yes.
well.
I know him because he served in the same committee as I serve in AIAA. He's a lot younger. Okay.
Yeah, he's
See,
quite a bit
I
younger.
see. As soon as you say where you graduate from, I kind of know some faculties from there. Well, good for you, Daniel. If you ever talk to them, say hello. But I'll try to find Paul. I haven't seen him ever since he graduated from Arizona State. I think it's probably I would say in the 80s. Okay.
Okay,
Well,
all right.
well, the fifth speaker, not the least one, actually, I know this speaker, Matthew Rukowski from Naval Research Laboratory. Matt received his PhD in inorganic chemistry from the University of South Carolina, 2002, and he's currently the acting head of advanced materials section within the chemistry division at Naval. Matt has been working as a synthetic materials chemist in the development of various high temperature resin, system, composite, and ceramic materials for 15 years. He has overseen numerous programs related to polymer composite to materials combat chemical warfare threats within the Department of Defense. He currently has 62 bronze paper and 52. Wow, Matt, impressive. U.S. patent. He also received several awards related to peer review, publication, and technology transfer. Matt's actual papers, high char, phenolnitride, resin blends. And I actually personally know Matt, and I actually been working with Matt for a few years. Matt, I'm going to ask you the question. Actually, one is, the improvement you found using pitch significantly in actually enough for targeted application for these concerned with the increase in porosity? Okay, Matt, here's the question. The first one. Could you answer that, Matt?
Yeah, no, I got it. Thanks, Joe. Thanks for the introduction thing. Yeah, so to answer that question as it relates to this presentation, a lot of this work was done initially just to see, obviously, char resins have been around for a long time, and we know that they char at high char yields, and that's well known. The real fact of the matter is it's ungraphitizable carbon. So even if it gets to 2000 C, it's not going to graphitize. It's highly aromatic. But the idea was, if using pitch as a additive, can you induce graphitization of this matrix at low temperatures, as discussed in this presentation, but more importantly at the higher temperatures, which was discussed at the NSMMS conference that just passed. So some of that information I can't really share here, but to answer that question, I think the reason why we had increased porosity is we're not expert in pitch chemistry. There are ways to stabilize pitch and to make it so that it basically do an oxidation step similar to polyacrylonitrile when they make furs, and it allows it to pseudo cross, and then therefore it doesn't vaporize as you're heating through the carbonization process. So that's we didn't force this out before we did this particular presented data. So we do believe that we can use it as an inclusion into this matrix, good properties at high temperature, and then not induce that's seen initially in this particular data was presented for SAMPE.
Anything else you want to hit, Matt, for question one?
No, not for that question.
All right. Let me ask you the second question. Were you surprised that the increase in pitch content resulted in marginal improvement in char yield?
To a certain extent, yes, but I do also believe that maybe it's so because the pitch wasn't stabilized fully, it's hidden by the fact that some of the pitch vaporized during the carbonization process. So it may be that the char yield can be a little bit higher, but we're all reaching the limit of, this, the char basically improved from, they say, the mid 70s to the upper 70s. And typically in high char yielding systems, you're getting pretty close to the limit of how much you're going to char. I mean, even in all the research that NRL has done over the years, the highest char yielding system we've ever had was about 85%. But the acetylene-based system that was highly, essentially 100% cross-linked, there was no groups that could actually fragment the carbonization process, so it actually was able to char higher. So to answer that question, I'm not surprised necessarily, but it can be improved by a few percent. But that few percent could actually be beneficial depending on the application, the final application that you're targeting.
Hey, Joe and Matt, this is Brianna. I have a question to kind of piggyback off that was submitted by an audience member. Matt, another question for you. So it seems like cracks in your char might be caused by really fast heating rate. Did you perform slower carbonization of your samples?
For this particular study, no. And I do agree that, yeah, if you really do slow down the carbonization process, we can achieve higher char. I do agree with that. And I think that is a study that's to be further investigated with our materials. Thanks for that.
Perfect. Another question from the same audience member. Usually C/C composites with pitch are made under pressure to avoid volatiles evolution destructing composite. Did you consider a pressure application for your processes to decrease porosity?
Yeah, we considered it. I mean, currently we don't have that capability. I mean, I don't have it in my actual laboratory, but that is a perfectly good explanation. That's a perfectly good process to do, even for retaining some carbon as you char just to meet some nitriles. That would probably be a beneficial process. So that is correct, and it's a good suggestion, and I do thank that. I thank you for asking that question.
Perfect. Thank you, Matt.
Sure.
I do have some questions because actually I know Matt's work. When you actually, when you're in your abstract, you said that you're actually heating the char yield at nitrogen. What heat, actually a heating rate we're using for that about 75%?
Well, I mean, so typically when we do like TGA studies like this, it's usually degrees a minute, so it is pretty high. But if we were to make, say, like larger samples, like specimens, we would to get up to 1,000 or 700,000, we would probably heat it around 1 degree a minute, and that's so it doesn't blow apart during the carbonization. But for small samples, it's 10 degrees a minute. It's kind of our standard, and it gives you it's a fast way to do it. You can do it within a couple hours, and then it gives you some indication of that you can compare different samples to one another.
I think one of the things that is said on the abstract is if you heat up to 1,500 degrees C, have you ever done that, Matt?
Yeah, we have, and it's probably no surprise to anybody that actually has worked on thionyl and any really highly aromatic systems. One of the things in a highly aromatic resin system, heating above 1,000, say up to 1,000, up to 1,500 C, maybe even 2,000 C, you shouldn't see much change in the overall char yield. You may see a few percent difference, but typically, once it's charred to 1,000, it's going to be retained above 1,000. Now, that's not typical for phenolic resins and resins that show somewhat high char at 1,000, but then they lose a significant amount above 1,000. So that's one of the advantages of the phthalonitriles in that they're easy to process and you're able to form this high char. That char is retained at really high temperatures.
Yeah, the reason why I have more questions for Matt is because I'm working with Matt on this particular actually PN system. And actually we are now working with in 2 programs using this PN system. So I think of all the 5 papers, this is the only one I actually know a little bit more than the other one. Okay. The PN system is actually a very high char yield, probably one of the second high char yield system in organic system I've ever dealt with. Okay, thank you, Matt. Appreciate that.
Sure, thanks, Joe.
You are most welcome. We use 48 minutes. What do you want us to do, Deanna?
That's up to you, Joe. If you want to ask one of the other questions, you can. But this session's been extremely entertaining, so we can stop it here if you want to conclude now.
You don't need to drag it to an hour because I think all speaker actually answered the question quite well, but I do actually have some other questions for actually some of the speakers if I actually read the paper. I haven't read it, but I think I'm going to go back and read some of the paper and I may send some questions. With that, I thank all the speaker and also actually for your contribution to this particular session. Do you have any questions for me?
Who don't you know, Joe?
Okay. If not, we're going to conclude this session and thank you very much for your participation. Have a good day. Bye-bye.
Thank you, everyone.
Thank
Bye-bye.
you.
Thank you.